Let's now study a case application. A database server is behind this application. To log on, a username, for example admin, and a password are needed. If you submit invalid data, the application will not log you in. We don't even know a valid username for this application. We can enter QWESD as login as well. The result would be the same. There's little chance that this username is found in the system. We'll now modify a command exactly as we showed you, directly in SQL. We need to end a string with an apostrophe, insert a condition that is always true, and mark the following part of the string as a comment. This trick comes off. You can even see that the username we're logged under is quite unusual. Because it is so simple and doesn't require modification of a source code, SQL injection is now one of the biggest perils persistent in internet and local networks. Let's come back to the case code. As we mentioned before, string concatenation may be done client-side or server-side without much difference. Let's see if this statement is accurate. We'll create a procedure with the username as the parameter in the call and a user's password as the second parameter. Both values are empty by default. For whatever reason, the developer has created the procedure in this way. Next, we'll declare a variable in the procedure body to which we'll construct an executable statement. Constructing the statement, we'll enter exactly the same values as before. We want to check if a correct username parameter has been submitted and if the password is also correct. At the end, we want to make the string executable. The exec statement is used for this purpose. Let's create this procedure. Now let's try to execute it again by maliciously submitting OR1 equals 1 minus minus instead of the username and password. The difference here is that we need to submit a different but always uneven number of apostrophes. The single quotes are always inside a procedure body and in the call. This has to be taken into account. Let's check the call for the procedure. Nothing has changed. Again, as a user, we can control program execution, or the results it returns, by submitting simple logical expressions. This attack can and should be avoided by, for example, not joining statement definition with parameters. In the case of MS SQL Database Server, a solution is provided by the use of execute SQL procedures instead of calling a string. The difference is that with this procedure, we have a statement that we want to execute, a definition of parameters, and a first and second parameter. Nothing can be summed up. Let's try to alter our procedure. Let's execute it again in the same way. The operation failed this time. Now the procedure must be called with two parameters of an expected type. If they are not supplied, the procedure fails. If the OR1 equals 1 expression is the parameter, there would be no problem. It's a parameter value. The SQL server knows this and doesn't link it in any way to an executed statement. Simple SQL injection can allow an attacker to log on to a database-served application without submitting a login and a password. You can enter an expression in this place that is always true and add a specified number of single quotes and double dashes at the end. As simple as that. But this attack technique offers a far wider range of possibilities. We'll be now executing statements directly on the side of a database server to see the results of the attack in real time and give the attack a little speed boost. We have no control over the code in rows 40 and 42. It could, for example, be embedded in an application code. It's a query that we've already performed 2 times before. The row we do have control over is row 41. To improve readability, double dashes are inserted at the beginning of row 42 and not at the end of row 41. Unfortunately, in this interface, an end-of-line marker affects the 2 dashes. We can enter only row 41, assuming that rows 40 and 42 are already entered. What does this mean for us? Firstly, we can of course read the contents of the table. If an application checking the query involves assuming that if a statement returns a row, this means the correct login and passwords were supplied, we're logged in. As we've seen, HackMe Travel does this. Being more inquisitive, we can also try to see if we can obtain some information about the structure of the database we're connected to. With this, we move on to a subject that we'll systematize later in theory. This is the so-called blind SQL injection. In this variant of the attack, the names of columns and tables are unknown. They can, however, be sorted by some criteria. We can, for example, order it by column 4. Or, as it turns out, we can't. If an application allows SQL injection and also returns users to an error message as reported by a database server, if one error is made, another can be made. This means that we're able to see that the table, its name is still unknown, does not have 4 columns. Does it have 3 columns then? Since the application reports no error, we can assume it does. This information can be obviously obtained in a number of other ways. Another solution would be, for example, to add the union select 1 clause. We'll add 1 to the result of the query. Query results must be tables in SQL. They have to be in a tabular format. There's an equal number of columns in all places in the table. Rows cannot be shorter or longer. By looking at an error message, you can see that 1 is not the correct column number. Two is not a good number either. We know already that there are 3 columns in the table. The application will return no error message in this case. It's high time to find the names of the 3 mysterious columns. Knowing them, they will constitute a point of entry to the entire database system. Let's try to enter the having 1 equals 1 expression. This logical test is applied to groups and not to rows. Grouping comes before selecting something out of a group. Let's see how the server will react to this query. Since we wanted to check something that should be grouped, the server tells us that the username column of the user table is not contained in a list of grouping columns, and is not a call parameter of an aggregate function such as sum either. This doesn't matter though. What's vital for us is that we know the names of the table and its column. What else can be obtained? We know that there are 3 columns. The next step is to obtain the name of another column. We'll use the available information, the error messages, to alter the query. We admit that we forgot to use the column for grouping. Let's see what happens after executing the following query. The server tells us that we forgot to include another column. Next, we execute a query that uses the information we've just received. The server's response is that there's another column that has not been included in the grouping. Using this information in another query, no further error messages will be prompted. At this point, the name of the table and the names of all the table columns are found. We've not even connected to the database. This information can be discovered simply by reading error messages. Now, if we can obtain the column data types, this would be quite enough. Let's give it a try. We already know the union clause. The aim of this operator is to combine results of queries. This time, we'll try to sum something that is contained in the username column. What will this produce? The username column cannot be summed up because the data type of the column is varchar. This is precisely the information we wanted to extract. The password column is likely to be the same, so we'll skip it. We'll check the result of summing for the third column. The result here is the bit data type. We have now acquired the name of the table, the names of the columns, and the column data types. It would also be good to see the contents of a given table. How can we do this? We know that there are 3 columns. The data type of the third is bit. Bit is a quite peculiar data type that stores a very limited range of values. It only takes a value of 0, 1, or null. The min username operation as the third column, the isAdmin column of the bit data type, should fail due to type incompatibility. Individual rows of a table should have the same number of columns, and columns should be of the same type in all places. Let's see what the server will return. Converting the value March into a bit data type failed. In this way, the name of the first user is discovered. You can use the same method to discover the password of the user. The password is password. How can you discover the logins and passwords of other users? You already know the credentials of one user. We'll use the same trick, but this time we don't want to find the data we already have acquired. The next user is Tomic. As you can probably imagine, obtaining the password for this user is a mere technicality. We'll take Marchin's password that was provided in an error message and request a next password. The second password is more secure. We now know all we needed to know. Perhaps if you wanted to use the company's services again, you might like to save time by quit writing OR1 = 1 and similar expressions over and over. You can add yourself to a user list. And since we can execute queries, we probably can execute insert commands as well. We know the name of the table and the names of the columns in the table. Now we can insert anything we want there. Something has happened. We don't know the details since we're connected through a web interface. We don't see results as clearly as in this presentation, but we can always check if there's a new row. Coming back to one of the earlier queries, it turns out that there's a new row. We can log as attacker using the password tour. We're so fortunate that it seems that we've become an administrator of the system. This technique could also be applied to other ranges of practices. This will be the introduction of the automated SQL injection attacks that will be covered soon.